So if we have a reaction mixture that's not at equilibrium and we have reactants and products present, how can we tell which direction the reaction is going to go? We use what's called the reaction quotient. So the reaction quotient, QC or QP, for concentration or pressure, it's calculated using the same expression as the equilibrium constant. The difference is that the reaction is not at equilibrium. So we're calculating this value with whatever concentrations we currently have. Okay? So K, equilibrium concentrations only. Q, whatever we've got. What's going to happen is the reaction is going to proceed either forward or backward until it gets to equilibrium. And at equilibrium, Q is equal to K. So let's look at this. Yes?
So when we see Q, do we assume it's not in equilibrium?
Right.
Okay.
Yeah, so if you're looking at a Q value, it's not at equilibrium. And the relative size of Q compared to K is what's going to tell us which direction it's going to go. Because it's going to change in a way that will make ultimately Q equal to K. So here we have reaction where blue circles are turning into red circles, right? And so down here, we're starting with 1 molar blue circles, those are A, and none of the B. So we have all reactants and no products. So if I were to calculate Q down here, I would have 0 over 1, right, which is 0. If I come over here and calculate Q, let's actually write these down. So at this point, Q equals 0 over 1, which is 0. Here, Q equals 0.25 over 0.75, which is 1/3, right? So as the reaction is going to the right, Q is getting bigger. It's getting closer to the actual K. The actual K, we're told here, is 1.45. So it will proceed with blue circles turning into red circles until those concentrations give us the equilibrium constant. So Q is equal to K. If we start over here with lots of red circles and very few blue circles, like over here at this, Q is equal to 0.75 over 0.25, which is 3. So over here, Q is too high, and over here, Q is too low, it's too small. So the reaction will go in the direction that makes Q get closer to K.
So can we assume that if Q is higher, then it's going to be a reverse action?
Yep.
And Q is small, it's going to be a forward action?
Yep. If Q is smaller than K, the reaction will go in the forward direction. If Q is larger than K, the reaction will go in the reverse direction until Q equals K. And then it's at equilibrium.
If you don't know what K is, how are you going to find? I mean,
Well, you have to know what K is.
but didn't you say that we use QP and QC when we don't know what the initials?
Well, we use those when we're not sure which direction the reaction is going to go.
Okay.
So I have this reaction, I throw in a bunch of reactants and products. I know what their concentrations are, but how do I know, is that going to make more products or is it going to make more reactants? Which direction is it going to go? I can compare the concentrations of the stuff that I threw in there, I can plug those into the expression and calculate Q and compare that to K. And that'll tell me, am I going to go forward or backwards? Because it has to change, right? So, ooh, almost dropped the Apple Pencil. It doesn't like it when I do that. If Q is too small, right, what has to happen is this number in the numerator has to get bigger, and the number in the denominator has to get smaller in order for Q to equal K. So I have to make more product and use up more reactant to get to K. Over here, I've got too much product and not enough reactant. Q is too big. In order for Q to get smaller, the reaction needs to go towards the reactants. I need to decrease the amount of product and increase the amount of reactant.
So you're saying that we're given K?
You would need to know what K is, yes. This is not a method for calculating K.
Okay, I think that's what I'm
Yeah.
trying to.
Okay, so what we're building up to is we know what K is, and we're going to use that to predict what the concentrations at equilibrium are, so we don't actually have to measure them.
Okay, that sounds better than.
Yeah.
We're just using Q when it's not at.
We use Q when it's not at equilibrium, and that tells us what direction it's going to go. So here's the summary of that. The reaction quotient relative to the equilibrium constant is the measure of the progress of a reaction toward equilibrium. When Q is smaller than K, the reaction goes to the right towards the products. When Q is larger than K, the reaction goes to the left towards the reactants. When Q equals K, the reaction is at equilibrium. At a given temperature, K has one value. It's the equilibrium constant. Okay? Q is not the reaction constant. It's the reaction quotient, and it's going to change. Q will change as the reaction proceeds, and it will approach K and ultimately equal K. So Q depends on the current state of the reaction, what are the reactant and product concentrations, and it has many, many different values as the reaction progresses. Any questions? Consider the reaction and its equilibrium constant. We have N2O4 in equilibrium with NO2, and Kc is equal to 5.85 times 10 to the minus 3 at some temperature. The reaction mixture contains NO2 concentration of 0.0255 molar and N2O4 0.0331 molar. Calculate QC and predict the direction in which the reaction will proceed. So I use the same expression as for K. So QC is the same fraction. So it's going to be the product, NO2, it has a coefficient of 2, so it's squared, divided by the concentration of the reactant. So I'm going to plug the values that I currently have into this expression. The NO2, 0.0255, that one is squared, divided by 0.0331. This is 0.0196.
So
It's going backwards. K is equal to 5.85 times 10 to the minus 3. It can be tricky when you compare a number in decimal notation and a number in scientific notation. So either make them have the same exponent on the 10 or put them both in decimal. So this would be 0.00. 0.585. So we see that QC is greater than KC. Reaction goes to left towards the reactants. Did you have a question?
When would you use K or when would you use Q?
So K is at equilibrium. K is something that you can look up in a book or on the internet or something. You can look it up. Other people have spent a lot of time measuring these things, right? And then you can know, I mean, you're in control of your reaction mixture, right? You know what you put in there. So you know what the concentrations are, right, when you stuck them in there. You calculate QC with the current concentrations. Q is the quotient, it's not at equilibrium yet.
Okay, so for Q, it says that it doesn't need to be at equilibrium.
Right.
So if it was at equilibrium.
If it is at equilibrium, you can still calculate Q, but it's going to have the same value as K.
So could you do ice with Q if it's at equilibrium?
Well, you could do an ice table, but Q at equilibrium, we would just call it K, because it's the same, yeah. Any other questions? It is kind of a weird idea.
So that just means that you need more of the reactant to reach equilibrium?
Yes, it means that in order for this fraction to become the equilibrium constant, to equal the equilibrium constant, I need this numerator to get smaller and the denominator to get bigger, because this number is too big. It needs to get smaller so that it matches this. Then we'll be at equilibrium. I don't have to add something to it. It's an equilibrium reaction. It's going to go there itself.
Is this more just looking at at what process is it at this point
Yeah.
with those concentrations?
I mean, a lot of times you're like, oh, why would we care? Well, what if this was an exothermic or endothermic reaction? Then if it went one direction, it would get hot, and if it went the other direction, it would get colder. You might care then, right? So for the reaction N2O4 in equilibrium with 2NO2, reaction mixture at a certain temperature initially contains both of those gases in their standard states, which means that their partial pressures equal 1 atmosphere. If you don't remember what standard states are, you can review section 7.9. If Kp is equal to 0.15, which statement is true of the reaction mixture before any reaction occurs? So we are told that Kp equals 0.15. What is Qp right now? It's 1 squared over 1, which is 1. The partial pressure of the product squared divided by the partial pressure of the reactant squared, just plain. So at their standard states, they're 1 atmosphere of pressure each, so Qp is 1. Is Q greater than or less than K? It's greater, right? So the reaction will go to the left, to the left, to the left. Any questions?